Okay, let's have an application of differential equations to electrical circuits. Okay, let's have this one. A 12-volt battery is connected to an LR series circuit in which the inductance is 0.5 Henry and the resistance is 10 ohms. Determine the current I if the initial current is 0. So this is the diagram. Okay, it is beyond the scope of this course to derive the differential equation involved, but we will just accept that the differential equation involved is L di dt plus Ri is equal to E. From the data, okay, this V is actually equal to what, 12 volts, and then this R is how much, 10 ohms, and this L is what, is 0.5 Henry, and then when T is 0, okay, our I is 0. So okay, this will be used to determine the value of the arbitrary constant in the solution of the dE. So okay, we have this LDI plus RI is E, where the data is L is 0.5, R is 10, and E is 12. Okay, plug all these values here in this equation. Okay, L is 0.5, di dt plus 10I is 12. Divide both sides by 0.5, that is di dt plus I. 10 over 0.5 equals 12 over 0.5. Of course, that's the same as di dt plus 20I is 24. This is a linear differential equation with P of t is 20 and P of t is 24. Okay, we compute the integrating factor. The integrating factor is e to the integral of P of t dt. That is e to the integral of 20 dt. Of course, that is equal to e to the 20t. And the solution of the differential equation is the integrating factor times I equals integrate the integrating factor times P of t, which is 24 dt. And integrating, okay, this is okay, you have to balance it, you have to divide that by 20, so this is going to be 24 over 20, that's 6 over 5, e to the 20t plus c. Divide both sides by e to the 20t, that is 6 over 5 plus c to the minus 20t. Now remember, we have this condition: when t is 0, I is 0, we can determine the value of c there. So solve for c given that I of 0 is 0, or when t is 0, I is 0. Okay, this is just repeated from here. Here I of t is 6 over 5 plus c e to the negative 20t, and substitute 0 is equal to 6 over 5 plus c e to the negative 20 times 0, and you can get the value of c. The value of c is negative 6 over 5. And plug it there in the original equation there. So here you have to plug it there. So you now have the function. Your I of t is given as 6 over 5 minus 6 over 5 e to the negative 20t. Okay, that means if you are given t, you can find I, or if you're given I, you can find t. Okay, let's have another application of differential equation to a series RC circuit. If a resistance of 2000 ohms and a capacitance of 5 times 10 to the negative 4 farad are connected in series with an EMF force of 100 volts, find the charge Q of t on the capacitor if Q of 0 is 0, and find the current at t equals 0.1 second. Okay, here is the diagram for a series RC circuit. Okay, so you're given E as Okay, you're given E as 1. This is what? This is uh, 100 volts. That is 100 volts. Okay, you're given the resistance as what? 2000 ohms. And you're given the capacitance as 5 times what? 10 to the negative 4 farad. Okay. Again, the derivation for the differential equation for this circuit is beyond the scope of this course. Instead, we're just going to accept this one. The relationship between Q and E is that R dQ dt plus 1 over CQ is equal to E. Okay, let's plug the values. Our R is 2000, our C is 5 times 10 to the negative 4, E is 100, and Q of 0 is 0. Plug it there. Okay, or plug, this is just repeated, plug the values. You have 2000 dq dt plus 1 over 5 times 10 to the negative 4q is 100. Okay, or divide both sides by 2000. If you divide both sides here by 2000, okay, this one is to be divided by 2000. Okay, uh, here you are going to divide both sides by 1 over 2000 there. So this will come out. You have what? You have dq dt plus q is 1 over 20. You notice that this is what? This is a linear differential equation in q. So our integrating factor, okay, let's just remove this is p of t. Okay, our given is p of t is 1 and q of t is 1 over 20. Integrating factor is again e to the integral of p of t dt, which is e to the integral of dt or e to the t. Your solution is the integrating factor times q is equal to the integral of the integrating factor plus times whatever is this value, which is q of t, 1 over 20 dt. Integrating, you have e to the tq is 1 over 20 e to the t plus c, and solving for q, dividing by e to the t, you have q of t is 1 over 20 plus c to the minus t. Now you have a condition that is what? Q of 0 is 0. That means when what? When t equals 0, okay, when t equals 0, your q is what? Your q is 0. So you can substitute it in this equation. You have 0 is equal to 1 over 20 plus c to the negative 0. Of course, this is what? This is 1. Okay, therefore, your c, okay, your c is e to the negative 120, and plug it there in that equation. You have q of t is 1 over 20 minus 1 over 20 e to the minus t. So we have answered the charge on the capacitor. This is defined by 1 over 20 minus 1 over 20 e to the minus t. But you're asked, find the current at t is 0.1 second. Now remember, okay, here, find the current at t is 0.1 second. Now remember that your I is equal to the derivative of q with respect to t. So all you have to do is get the derivative of this function with respect to time, and you get I. So your q of t is again 1 over 20 minus 1 over 20 e to the minus t. And getting the first derivative, that is, okay, this is constant. This is just negative 1 over 20 times negative 1 e to the minus t, that becomes positive. positive. So negative 1 over 20 times negative 1. That's 1 over 20 e to the minus t, and just substitute t is 0.1 second. So this is the answer. This is the model. I of t is 1 over 20 e to the minus t, and I of 0.1 is just plug 1 over 20 e to the negative 1, and your answer is 0.045244 amperes. Okay, this is the answer for this problem.